Hello there, and welcome to Behind the Space. I'm really glad you're here with me tonight. Maybe you've had one of those days where your mind has been racing from one thing to the next, never quite settling. Or perhaps you're the kind of person who finds comfort in contemplating the vastness beyond our world, in letting your thoughts drift among distant stars and swirling galaxies instead of the concerns of daily life. Whatever brought you here, this journey is for you. Tonight, we're going to travel together through the greatest story ever told. Not a story written in books or passed down through generations, but one written in light itself, in the motion of galaxies, in the faint whisper of radiation that fills every corner of space. We're going to explore the story of the universe, from its fiery beginning to the present moment, and perhaps catch a glimpse of what lies ahead in the vast ocean of time still to come. You don't need to do anything but relax. Let your shoulders drop. Let your breathing find its own natural rhythm. As we move through this cosmic narrative, let the images form in your mind, like constellations taking shape in a dark sky. We'll take our time, exploring not just the facts and figures, but the profound mystery and wonder that surrounds it all. The question that started everything. There's a question that sits at the heart of human curiosity, one that every culture and civilization has asked in its own way. It's deceptively simple, just a handful of words, yet it contains within it the seeds of all science, all philosophy, all wonder. Where did everything come from? Look around you right now. The walls of your room, the device you're watching this on, the air you're breathing. Zoom out further in your mind. The ground beneath you, the planet spinning through space, the sun burning at the center of our solar system, the hundreds of billions of stars in our galaxy alone. Go further still, the countless galaxies scattered across observable space like islands in an infinite ocean. All of it, every single atom, every particle of light, every force and field. Where did it all come from? For most of human history, this question was the domain of myth and theology. Different cultures told different stories, each beautiful in its own way. Each attempting to grasp at something fundamentally beyond ordinary experience. The universe emerged from a cosmic egg, or from the body of a primordial giant, or from the word of the Creator speaking light into darkness. These weren't just stories. They were humanity's first attempts to make sense of existence itself. But something remarkable happened in the 20th century. Science, which had been steadily peeling back the layers of nature's mysteries, finally reached far enough to touch this most fundamental question. Not with myth or metaphor, but with mathematics, observations, and evidence. What emerged wasn't a complete answer. Perhaps it never will be. But it was something extraordinary nonetheless. A narrative based on light from distant galaxies, on the behavior of atoms in laboratories, on the faint afterglow of creation itself still visible in the night sky. The story that science tells about the universe's origin is called the Big Bang Theory. Though, as we'll discover, that name is somewhat misleading. It suggests an explosion, a blast of matter flying outward from some central point. But what actually happened was stranger and more profound than any explosion. It was the beginning of space itself, the birth of time, the emergence of everything from a state so extreme that our current physics can barely describe it. This isn't just ancient history we're talking about. The universe is still telling us its story, every single moment. When astronomers point their telescopes at distant galaxies, they're looking backwards in time, seeing those galaxies as they were millions or billions of years ago. The light that left them has been traveling across space all that time, carrying with it information about the early universe. In a very real sense, the past is still visible, still accessible, if we know where and how to look. And we've gotten remarkably good at looking. Over the past few decades, our technology has reached a point where we can observe galaxies that formed when the universe was just a few 100 million years old. Barely out of its infancy, we can detect the faint radiation left over from when the cosmos first became transparent to light. We can measure the exact composition of matter, forged in the first moments after everything began. Each observation is like finding another page in a book written in fire and light. A book that tells the story of how we came to be. But before we dive into the details, before we explore the physics and the observations, let's step back and appreciate what we're really doing here. We're taking a journey through time itself. We're going to watch the universe emerge from an unimaginably hot, dense state. We'll see the first atoms form, the first stars ignite, the first galaxies take shape. We'll trace the path that led from that primordial fireball to the rich, complex, beautiful cosmos we inhabit today. And we'll do it all while floating here in the present moment, contemplating mysteries that span billions of years. So settle in. Let your mind expand to hold these vast scales of time and space. We're about to begin at the beginning, or at least as close to it as human knowledge can currently reach. The discovery that changed everything. Our story really begins not with the Big Bang itself, but with a discovery made in the early 20th century that fundamentally changed how we understand the cosmos. For thousands of years, humans had looked up at the night sky and assumed what they saw was eternal and unchanging. The stars seemed fixed in their patterns. The universe appeared static, a stage on which events unfolded but which itself never changed. Then came Edwin Hubble. In the 1920s, working at the Mount Wilson Observatory in California, Hubble was studying distant galaxies through what was then the most powerful telescope in the world. He was particularly interested in something called redshift, a phenomenon where the light from these galaxies appeared stretched toward the red end of the spectrum. This stretching happens when the source of light is moving away from the observer, similar to how the pitch of a siren drops as an ambulance speeds past you. What Hubble discovered was astonishing. Not only were distant galaxies receding from us, but the farther away a galaxy was, the faster it appeared to be moving. This wasn't random motion. It was a pattern, a relationship that held true across the entire observable universe. Galaxies weren't just drifting through space, scattered by some ancient explosion. Space itself was expanding, carrying the galaxies along with it, like raisins in rising bread dough. Imagine you're an ant living on the surface of a balloon. As someone inflates the balloon, every other ant on the surface appears to move away from you. The farther away another ant is, the faster it seems to recede. That's because the rubber between you is stretching. The ants aren't walking through the rubber, they're being carried by its expansion. Hubble's discovery suggested that our universe works similarly. with galaxies as the ants and space itself as the stretching rubber. This revelation was so profound that even Albert Einstein initially resisted it. Einstein had developed his general theory of relativity about a decade earlier, a mathematical framework that described gravity not as a force but as the curvature of space and time. When he first applied these equations to the universe as a whole, they suggested something that seemed absurd to him. The universe should be either expanding or contracting. It couldn't just sit still. This bothered Einstein so much that he added a term to his equations, something he called the cosmological constant, specifically to force the universe to remain static. It wasn't that the mathematics required this term. It was that Einstein's philosophical assumptions about the cosmos demanded it. The universe, he believed, had to be eternal and unchanging. But Hubble's observations changed everything. When the evidence became undeniable that the universe was indeed expanding, Einstein reportedly called his insertion of the cosmological constant his greatest mistake. The universe wasn't static. It was dynamic, evolving, changing with time. And if it was expanding now, that meant something extraordinary. Run the clock backwards, and everything gets closer together. Keep going back in time, and the universe becomes denser, hotter, more compressed. Eventually, you reach a point where all the matter and energy we see around us today was packed into an incredibly small, incredibly hot, incredibly dense state. This was the birth of the Big Bang Theory, though that name wouldn't come until later. And here's something fascinating about the expansion. When we say space is expanding, we really mean it literally. It's not that galaxies are flying through a pre-existing empty space. The space between them is actually growing, being created, stretching like fabric. This is why distant galaxies can appear to move away from us faster than the speed of light without violating Einstein's rule that nothing can travel through space faster than light. They're not moving through space that fast. Space itself is expanding, carrying them along. Think about what this means for our understanding of the universe. Every galaxy we see was once much closer to every other galaxy. Go back far enough, and there was a time when all the matter in the observable universe, everything that would eventually become hundreds of billions of galaxies, was compressed into a region smaller than a single atom today. The temperature was so high that atoms couldn't exist. The density was so great that space and time themselves behaved in ways that our current physics struggles to describe. This expansion has been happening for approximately 13.8 billion years. That's the age of the universe, not measured by counting years on some cosmic calendar, but derived from observations of how fast space is expanding and calculations of how long it would take to reach the current state from that initial hot, dense beginning. It's a number that comes from multiple independent lines of evidence, all pointing to the same conclusion. The discovery of the expanding universe was just the first piece of evidence for the Big Bang Theory. Over the following decades, more observations would pile up, each one confirming and refining our understanding. But Hubble's insight was the crucial first step. It transformed the cosmos from something eternal and unchanging into something with a history, a story, a narrative arc stretching from an explosive beginning to an uncertain future. And here's the beautiful thing. The universe is still expanding right now, in this very moment. As you breathe in and out, space itself is growing. Distant galaxies are moving farther apart. The story isn't over. We're living in the middle of it, participants in a cosmic drama that's been unfolding for nearly 14 billion years. The earliest moment we can describe. Now we come to the heart of the mystery, the moment that started it all, or more accurately, the earliest moment we can say anything meaningful about. When people talk about the Big Bang, they often imagine a point in time when everything suddenly appeared, when existence itself switched on like a light. But it's more nuanced than that and more strange. The truth is, we don't know what happened at the very beginning, if such a concept even makes sense. What we do know is that there was a time, incredibly early in the universe's history, when everything we can observe today was compressed into a state of such extreme density and temperature that our current understanding of physics breaks down, not because there's nothing to understand, but because our mathematical tools, our theories, our equations all stop working. They produce infinities and impossibilities, mathematical signals that we've reached the edge of our knowledge. The earliest moment we can meaningfully describe is called the Planck epoch. It extends from the beginning, whatever that was, to about 10 to the power of negative 43 seconds after the start. That's a decimal point followed by 42 zeros, and then a 1. In other words, a time scale so brief that it makes a nanosecond seem like an eternity. If you tried to fit the Planck epoch into the entire 13.8 billion year history of the universe, it would be like comparing the width of a single atom to the distance across our entire galaxy. It's almost inconceivably small. During the Planck epoch, the universe was unimaginably hot and dense. We're talking about temperatures of 10 to the power of 32 degrees Kelvin. For context, the core of our Sun is about 15 million degrees. The Planck temperature is a trillion times hotter than that. At these temperatures, matter as we know it couldn't exist. There were no atoms, no atomic nuclei, not even individual protons or neutrons. Just a seething foam of energy and exotic quantum fluctuations. Even more remarkably, all four of the fundamental forces that govern our universe today, gravity, electromagnetism, the strong nuclear force that holds atomic nuclei together, and the weak nuclear force responsible for certain types of radioactive decay. These forces are thought to have been unified during the Planck epoch. They weren't just acting together, they were genuinely indistinguishable from each other, aspects of a single superforce that we don't yet fully understand. This is where the phrase singularity often comes up in popular accounts of the Big Bang. A singularity is a point where mathematical equations produce infinite values, a breakdown of our ability to predict or describe what's happening. General relativity, Einstein's theory of gravity, seems to point toward a singularity at the beginning of the universe, a point of infinite density and infinite curvature of space. But here's the thing. Most physicists don't actually believe there was a true singularity. Infinities in physics are usually signs that our theory is incomplete, that we're trying to apply it to a situation where it doesn't work. What we're really dealing with is a frontier, a boundary beyond which our current understanding cannot penetrate. The Planck epoch represents the earliest time we can describe with any confidence using the physics we currently understand. To go earlier, to truly describe what happened at the absolute beginning, we would need something we don't yet have, a theory of quantum gravity. This would be a framework that successfully combines Einstein's general relativity, which describes gravity and the large-scale structure of space and time, with quantum mechanics, which describes the behavior of matter and energy at the smallest scales. These two theories are both extraordinarily successful in their respective domains, but they're also fundamentally incompatible with each other in their current forms. Reconciling them is one of the greatest challenges in modern physics. Various candidates for a quantum gravity theory exist: string theory, loop quantum gravity, and others each offer different approaches to the problem. But none of them are complete, and none have been confirmed by experimental evidence. Until we solve this puzzle, the very earliest moments of the universe remain shrouded in mystery. We can approach the boundary. We can describe what likely happened immediately after, but we can't quite see past it. Yet even with this limitation, what we do understand is remarkable. As the universe expanded and cooled beyond the Planck epoch, the forces began to separate, to differentiate from one another in a process called symmetry breaking. Imagine a perfectly smooth round ball sitting at the top of a hill. It's in a symmetric state, equally likely to roll down in any direction. But the moment it starts to roll, the symmetry breaks. It chooses one direction, and from that point on, the situation looks different depending on where you're standing. Something similar happened in the early universe. First, gravity split off from the other forces, becoming distinct and separate. Then, as expansion and cooling continued, the strong nuclear force peeled away. Finally, the electromagnetic force and the weak nuclear force, which had been unified into something called the electroweak force, separated into the two distinct forces we observe today. Each of these transitions happened at specific energies and temperatures as the universe cooled, like water transforming from steam to liquid to ice as it cools. Except instead of changing the state of matter, these transitions changed the fundamental structure of physical law itself. The Planck time, brief as it was, represents a horizon. We can't see past it with our current knowledge, but we can describe with increasing confidence what happened immediately after. And what happened next was perhaps the most dramatic event in cosmic history, a period of expansion so rapid, so extreme, that it defies ordinary intuition. We call it cosmic inflation, and it set the stage for everything that followed. The inflationary epoch. After the Planck epoch, as the forces began their gradual separation, something extraordinary happened. Something so rapid and dramatic that it reshaped the entire nascent universe in a fraction of a second. This is the period known as cosmic inflation, and is one of the most important and fascinating chapters in the early universe's story. Inflation refers to a period when the universe didn't just expand, it ballooned outward at an exponential rate. We're talking about space itself growing faster than the speed of light, doubling in size over and over again in timeframes so brief they're almost impossible to conceptualize. The entire observable universe today, everything we can see in any direction, may have grown from something far smaller than a single atom to roughly the size of a grapefruit in about 10 to the power of -35 seconds. That's a decimal point followed by 34 zeros and then a 35. To put this in perspective, if you took a marble and expanded it at the same rate, it would grow to become larger than the observable universe in that same fraction of a second. It's growth on a scale that seems more like science fiction than science fact, and yet the mathematics works and the predictions match what we observe. Why did this happen? The leading explanation involves something called the inflaton field, a hypothetical quantum field that filled space in those earliest moments. Think of it as an energy embedded in the vacuum itself, not matter or radiation. but a property of empty space. When this field was in a particular high-energy state, it acted like a kind of anti-gravity, driving space to expand at an exponential rate. Now, you might be thinking, wait, doesn't this violate Einstein's rule that nothing can travel faster than light? The answer is subtle but important. The speed limit set by relativity applies to objects moving through space, but space itself can expand at any rate. It's not matter racing through pre-existing space. It's the fabric of space itself stretching, carrying everything along with it. Imagine drawing dots on a balloon and then inflating it rapidly. The dots aren't moving across the rubber. The rubber between them is expanding, causing them to separate. Inflation solves several puzzling problems that cosmologists noticed when trying to understand the universe without it. One is called the horizon problem. When we look in opposite directions in the sky, at regions of space that are so far apart they couldn't possibly have ever exchanged light or information in the age of the universe, we find that they look remarkably similar. They have almost exactly the same temperature, the same density, the same properties. How did they know to be so similar if they were never in contact? Inflation provides an elegant answer. Before inflation, these regions were much closer together. They were in contact. They had time to even out, to reach the same temperature and conditions. Then inflation happened, stretching space so rapidly that regions which had been neighboring suddenly found themselves on opposite sides of the visible universe, separated by distances so vast that light hasn't had time to cross between them since inflation ended. They look similar because they came from the same initial patch of space. Another problem that inflation solves is the flatness problem. Space can be curved, like the surface of a sphere, or flat, like a sheet of paper. Observations tell us that the universe today is remarkably close to being perfectly flat on the larger scales. But in the early universe, without inflation, any tiny deviation from perfect flatness would have been amplified rapidly as time went on. The fact that we see a flat universe today suggests that it must have been extraordinarily flat early on, fine-tuned to an absurd degree. That seems unlikely, as if someone carefully set up the initial conditions just right. Inflation solves this by stretching space so dramatically that any initial curvature is smoothed out, like stretching a wrinkled sheet until it appears flat, no matter what the curvature was before inflation. The exponential expansion would have flattened it out. When you zoom in close enough on a sphere, even a small sphere, it starts to look flat. Inflate the universe enough, and the same principle applies. Perhaps most remarkably, inflation may have created the seeds for all the structure we see in the universe today. At the quantum scale, space itself is never perfectly smooth. It undergoes tiny random fluctuations, quantum jitters that are normally too small to matter. But during inflation, these microscopic fluctuations were stretched to cosmic scales. A quantum fluctuation that started out smaller than an atom was blown up to sizes larger than galaxies, frozen into the fabric of space itself. These stretched-out quantum fluctuations created tiny variations in density from one region to another. In some places, matter ended up being very slightly denser than average. In others, slightly less dense. The differences were minuscule, just 1 part in 100,000. But they were enough. Over hundreds of millions of years, gravity would amplify these tiny variations, pulling matter together in the denser regions, allowing them to grow even denser, until eventually they collapsed into the first stars, the first galaxies. The great cosmic web of structure we observe today. It's profound to think about. The largest structures in the universe, the clusters and superclusters of galaxies, the vast filaments of matter stretching across hundreds of millions of light years, all trace their origins back to quantum fluctuations during inflation. The very small gave rise to the very large random quantum events that became the seeds of cosmic destiny. After a brief but intense period, inflation ended. The inflation field decayed, dumping its enormous energy into the universe in a process sometimes called reheating. This created a hot, dense soup of particles and radiation, and from here, the universe entered what we typically think of as the hot Big Bang phase. The era of exponential expansion was over, but the universe continued to grow, now at a more sedate pace. Matter, energy, and radiation filled space in all directions, and the stage was set for the next chapter, the formation of the first atomic nuclei. Inflation remains one of the most successful theories in cosmology, explaining multiple otherwise puzzling observations with a single elegant mechanism. Yet it's still somewhat speculative. We don't have direct proof that inflation happened, though the evidence is compelling. Scientists are searching for distinctive signatures that inflation would have left behind, particularly in the polarization patterns of the cosmic microwave background radiation. If these patterns are found, they would provide the smoking gun, direct evidence that space once expanded faster than light itself in those earliest moments after the beginning. When matter first formed, as the universe emerged from the inflationary epoch, reheated by the decay of the inflaton field, it found itself in a state that was still unimaginably extreme by our standards, but considerably cooler and less dense than during the Planck epoch. This was a crucial moment in cosmic history, because it's when the first lasting matter began to form. During the first fractions of a second, the universe was filled with what physicists call a quark-gluon plasma. Quarks are the fundamental particles that make up protons and neutrons. Gluons are the particles that carry the strong nuclear force. At incredibly high temperatures, these particles exist freely, unbound to each other, bouncing around in a chaotic soup of energy. But as the temperature dropped below a certain threshold, about 2 trillion degrees Kelvin, something remarkable happened. The quarks began to stick together in groups of 3, forming the protons and neutrons that make up the nuclei of atoms. This process happened when the universe was about 1/1,000,000th of a second old. In that brief moment, the building blocks of all future atomic matter suddenly came into existence. Every proton in your body, every proton in the sun, in the planets, in the distant galaxies, they all formed during that microsecond of cosmic time nearly 14 billion years ago. But here's something puzzling that scientists are still working to fully understand. According to the laws of physics as we know them, matter and antimatter should have been created in equal amounts during these early moments. For every proton, there should have been an antiproton. For every electron, a positron. When matter and antimatter meet, they annihilate each other completely, transforming back into pure energy. So here's the mystery. If equal amounts were created, and if they annihilated each other, there should be no matter left. The universe should be nothing but radiation. Yet obviously, that's not what happened. We exist. Galaxies exist. There's an enormous amount of matter in the universe and very little antimatter. Somehow, in those earliest moments, matter gained a tiny edge. Perhaps one extra matter particle for every billion matter-antimatter pairs. After all the annihilations were done, after matter and antimatter had destroyed each other in vast quantities, that tiny excess remained, and from that small leftover fraction came everything we saw. Every star, every planet, every atom in your body exists because of this subtle imbalance. This is called baryonic asymmetry, and it's one of the most profound unsolved puzzles in physics. What caused it? Why did matter win out over antimatter? Several theories have been proposed. Some suggest that the laws of physics themselves aren't perfectly symmetric, that there are subtle differences in how matter and antimatter behave. These differences have been observed in particle physics experiments, phenomena called CP violations, but not yet in a way that fully explains the scale of the imbalance we see in the universe. Other theories propose that heavy, exotic particles that no longer exist may have decayed asymmetrically in those earliest moments, favoring matter over antimatter by just the right amount. These hypothetical particles would have existed only briefly before vanishing, leaving only their influence behind. If they existed at all, we may never be able to observe them directly. We can only infer their presence from the effects they had on the infant universe. As the universe continued to expand and cool, reaching temperatures of around 1 billion degrees Kelvin, another crucial process began. This happened when the cosmos was about 1 minute old, and it's called primordial nucleosynthesis, with protons and neutrons now stable, and the temperature finally low enough for them to stick together without immediately being torn apart by radiation. The first atomic nuclei began to form. Protons and neutrons combined through nuclear fusion, the same process that powers stars today. The simplest nucleus, hydrogen, is just a single proton, but some protons and neutrons combined into deuterium, an isotope of hydrogen with 1 proton and 1 neutron. Some deuterium nuclei then fused into helium with 2 protons and 2 neutrons. A small amount of helium-3 with 2 protons and 1 neutron also formed, along with trace amounts of lithium. This primordial nucleosynthesis lasted for only about 3 minutes. After that, the universe had cooled and thinned enough that nuclear fusion stopped. The brief window of opportunity had closed. What emerged from this 3-minute span was a universe with a very specific chemical composition, about 75% hydrogen, about 25% helium, and tiny trace amounts of other light elements. This prediction of the Big Bang theory has been tested against observations, and the match is extraordinary. When we measure the abundance of hydrogen and helium in the oldest objects in the universe, objects that formed before stars had time to change the chemical composition much, we find exactly these ratios. It's one of the most powerful pieces of evidence for the Big Bang model. A prediction made based on theoretical calculations that's confirmed by what we actually observe in the cosmos. All the heavier elements, the carbon, oxygen, nitrogen, iron, everything that makes up the rich chemistry of planets and life, none of that existed yet. Those elements would have to wait. They would be forged much later in the cores of stars and scattered into space when those stars died. But the basic building blocks, the hydrogen and helium that would eventually collapse to form the first stars, came from this brief period of primordial nucleosynthesis. Even with atomic nuclei now formed, the universe was still far too hot for electrons to settle into stable orbits around these nuclei. The energy of the radiation was so great that any time an electron tried to bind to a nucleus, it would immediately be knocked free again by a high-energy photon. This meant that space was filled with a plasma of charged particles, electrons and nuclei moving freely, and this plasma was opaque to light. Photons couldn't travel far before bouncing off a charged particle. The universe glowed with incredible brightness, but it was like being inside an intensely bright fog. You couldn't see through it. This state would persist for hundreds of thousands of years, a long, quiet period where the universe continued to expand, continued to cool, but remained this glowing, opaque plasma. Nothing much happened during this time, at least not that we can observe directly. But patience is a virtue in cosmic evolution. Eventually, the temperature would drop low enough for a crucial transition to occur, one that would transform the universe from opaque to transparent, and in doing so, release a signal that we can still detect today. A signal that has become one of our most powerful tools for understanding the early cosmos. The oldest light we can see. Roughly 380,000 years after the Big Bang, the universe had cooled to a temperature of about 3,000 degrees Kelvin. Still hot by any everyday standard, but cool enough for something momentous to happen. For the first time, electrons could settle into stable orbits around atomic nuclei without immediately being knocked free. Protons capture electrons to form neutral hydrogen atoms. Helium nuclei capture electrons to become neutral helium atoms. This process is called recombination, though the name is slightly misleading because the electrons weren't recombining with nuclei so much as combining with them for the first time. This transition had a profound effect on the universe. Once atoms became neutral, they no longer interacted strongly with light. Photons that had been bouncing from particle to particle, trapped in an endless pinball game, suddenly found themselves free to travel through space unimpeded. The universe became transparent, and the first light began streaming through the cosmos in every direction. That light is still traveling today. We call it the cosmic microwave background, or CMB for short, and it's the oldest light we can possibly see. It's not tied to any star or galaxy. It comes from everywhere, filling space uniformly in all directions like a faint glow. Because of the expansion of the universe over the past 13.8 billion years, the wavelength of this light has been stretched enormously, shifted from visible light into the microwave part of the spectrum. It's become much cooler and fainter, now corresponding to a temperature of just 2.7 degrees above absolute zero. But it's still there, a direct signal from when the universe was in its infancy. The discovery of the cosmic microwave background is one of the great stories in the history of science, a tale of accidental discovery that turned into revolutionary confirmation. In 1965, two radio engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing a sensitive antenna designed for satellite communications. They kept picking up a persistent noise, a hiss that came from every direction in the sky equally, no matter where they pointed their antenna or what time of day or year it was. They exhausted every reasonable explanation. They cleaned out bird droppings from the antenna, thinking maybe that was the source of the interference. They checked for human-made radio signals. Nothing explained the signal. Meanwhile, just a few miles away at Princeton University, a team of physicists led by Robert Dicke had been working on the theoretical prediction that such cosmic background radiation should exist if the Big Bang theory were correct. When the two groups connected, it became clear that Penzias and Wilson had stumbled upon one of the most important discoveries in cosmology. They had detected the afterglow of creation itself. This discovery transformed the Big Bang from a speculative idea into established science. You couldn't have this cosmic microwave background without a hot, dense, early universe that cooled and became transparent. It was direct, tangible evidence that the universe had a beginning and has been expanding and cooling ever since. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for this discovery. When scientists first studied the CMB in detail, they found it to be remarkably uniform. No matter which direction you look in the sky, the temperature is almost exactly the same, varying by less than 1 part in 100,000. This uniformity itself was evidence for the Big Bang model. But as instruments became more sensitive, they detected tiny fluctuations, spots that were slightly hotter or cooler than average by just millionths of a degree. These tiny temperature variations are incredibly important. They represent small differences in the density of matter in the early universe. In regions that were slightly denser, there was slightly more matter pulling on the photons as they escaped, cooling them slightly and making them appear a tiny bit redder. In slightly less dense regions, the opposite effect occurred. These density variations are the seeds of structure, the beginnings of what would eventually become galaxies and galaxy clusters. Several space missions have mapped the cosmic microwave background in exquisite detail. The Planck satellite, launched by the European Space Agency in 2009, produced the most detailed map we've had until very recently, showing these temperature fluctuations across the entire sky. From these maps, scientists can extract an enormous amount of information about the early universe. The size and distribution of the hot and cold spots tell us about the density of matter, the amount of dark matter, the presence of dark energy, the age of the universe, and even the geometry of space itself. The latest observations from ground-based telescopes like the Atacama Cosmology Telescope in Chile and the South Pole Telescope have refined these measurements even further. In recent years, scientists have detected patterns that hint at the nature of dark energy, and have confirmed that the universe is indeed remarkably flat on the largest scales, just as inflation predicted. One of the most stunning results from studying the CMB is that we can now say with high confidence that ordinary matter, the stuff that makes up stars, planets, and people, comprises only about 5% of the total energy content of the universe. About 27% is dark matter, invisible material that we can only detect through its gravitational influence. And a full 68% is dark energy, a mysterious force causing the expansion of the universe to accelerate. The cosmic microwave background represents a boundary of sorts. It's the farthest back in time we can see using light. Everything before recombination is hidden behind this glowing wall of plasma. To peer further back, we would need something other than electromagnetic radiation. Some scientists hope to detect gravitational waves from the earliest moments of the universe, ripples in space-time itself that would have been created during inflation. These waves would pass right through the opaque plasma and could carry information from even earlier times. Others look for patterns in particles called neutrinos, ghostly particles that barely interact with matter and could also carry information from the pre-recombination universe. But for now, the CMB marks our observational horizon. And yet, what a horizon it is. When you realize that you're looking at light that has been traveling through space for 13.8 billion years, light that was released when the universe was just a tiny fraction of its current age, light that carries encoded within it the seeds of all future structure. It's hard not to feel a sense of profound connection to something vastly larger than ourselves. The universe wasn't just a distant abstraction. It was once a glowing fog of hydrogen atoms. No stars yet, no galaxies, just the potential for everything waiting to unfold, and encoded in that ancient light, stretched and cool but still present, is the story of how we came to be. The long, dark night. After the bright glow of recombination faded, after the last photons escaped and began their journey across space, the universe entered a period that cosmologists call the Cosmic Dark Ages. It's a beautifully evocative name for an era that, true to its name, was dark indeed. During this time, the universe was filled with neutral hydrogen and helium gas, drifting through expanding space. The photons from the Big Bang still existed, of course, but they had been stretched by expansion into the infrared and beyond, no longer visible as light. And crucially, no new sources of light had yet appeared. There were no stars, no galaxies, no glowing clouds of gas. The cosmos was vast, expanding, filled with matter, and utterly dark. If somehow you could have existed during this period and looked around, you would have seen nothing, perfect blackness in every direction. No stars to orient yourself by, no planets, no sign of structure or life anywhere in the vast expanse. Just darkness, silence, and the slow, patient work of gravity. This dark age lasted for hundreds of millions of years. It might sound like a period where nothing happened, but in truth, this was a time of quiet preparation. The tiny density fluctuations seeded during inflation, the ones that showed up as temperature variations in the cosmic microwave background, those were starting to do their work. In regions where matter was slightly denser, gravity was slightly stronger. These regions pulled in more matter from their surroundings, becoming denser still. As they grew denser, their gravity grew stronger, and they pulled in even more material. It's a positive feedback loop, a process called gravitational collapse, and it's the fundamental mechanism by which structure forms in the universe. Over millions of years, these overdense regions grew into vast clouds of hydrogen gas, some containing hundreds of thousands or even millions of times the mass of our Sun. These clouds were dark, cold, and slowly contracting under their own gravity. But as they contracted, something interesting began to happen. The gas in the center, compressed by the weight of all the material above it, started to heat up. This is a fundamental principle in physics. When you compress a gas, it heats up. When it expands, it cools down. You can feel this yourself if you've ever used a bicycle pump. The pump gets warm as you compress the air inside. The collapsing gas clouds work the same way, only on a vastly larger scale. As more and more material fell inward, the central regions grew hotter and denser. Eventually, after perhaps 100 million years or more of this slow collapse, the centers of these clouds reached a critical threshold. The temperature climbed to around 10 million degrees Kelvin. And the density became high enough that hydrogen nuclei, protons, began to collide with enough energy to overcome their mutual electrical repulsion and fuse together. Nuclear fusion had begun, and with it, the first stars were born. These first stars, what astronomers call population 3 stars, were likely very different from most stars we see today. They formed from pure hydrogen and helium, the primordial mix left over from the Big Bang, with no heavier elements to speak of. This matters because heavier elements help cool clouds of gas, allowing them to fragment into smaller pieces and form smaller stars. Without those elements, the first clouds remained hotter and formed much larger, more massive stars. Some of these first stars may have been 100 times more massive than our Sun, even more in some cases. They would have burned incredibly bright and incredibly hot, pouring out enormous amounts of ultraviolet radiation, but they also would have lived fast and died young. While our Sun will burn for about 10 billion years, these massive first stars might have lasted only a few million years before exhausting their fuel. When they died, they likely went out spectacularly. The most massive ones would have exploded as supernovae, titanic blasts that briefly outshone entire galaxies. These explosions scattered the material of the star, including newly created heavy elements forged in the star's core and in the explosion itself, out into space. For the first time, the universe now contained carbon, oxygen, nitrogen, iron, and all the other elements that would eventually make planets and life possible. Some of these first stars may have been so massive that they collapsed directly into black holes without exploding at all, creating some of the first black holes in the universe. Others may have undergone even more exotic fates, perhaps exploding with such violence that they left nothing behind, destroyed completely by their own death throes. As more and more of these first stars ignited, they began to change their environment. Their intense ultraviolet radiation stripped electrons from nearby hydrogen atoms, turning neutral hydrogen back into an ionized plasma. Each star created a bubble of ionization around itself, a region where the gas was no longer neutral but charged and transparent to light. This process is called reionization, and it didn't happen all at once. The first stars formed in clusters in the densest regions of the cosmic web, and their bubbles of ionization were like scattered islands in a dark sea. But over hundreds of millions of years, more stars formed, more bubbles appeared, and gradually these bubbles grew and merged. Like foam expanding to fill a space, the ionized regions grew until they overlapped, until nearly all the hydrogen in the universe had been reionized. By the time the universe was about 1 billion years old, reionization was essentially complete. The cosmic dark ages were over. The universe was lit once again, now not by the diffuse glow of the Big Bang, but by the concentrated light of countless stars. Structure had emerged from chaos, complexity from simplicity, and the stage was set for the next great chapter, the formation of galaxies. Recent observations from the James Webb Space Telescope have given us our first direct glimpses of galaxies that formed during this era. Launched in late 2021, this infrared observatory can detect light from some of the earliest galaxies, objects so distant that their light has been traveling toward us for over 13 billion years. These galaxies appear small, compact, and irregular, nothing like the grand spirals we see in the nearby universe today. They're more like building blocks, proto-galaxies that would eventually merge and grow into larger structures. What's remarkable is that some of these early galaxies appear to be more massive and more mature than expected, containing more stars than theoretical models had predicted could form so early. This has led to some exciting puzzles and debates in cosmology. It doesn't overturn the Big Bang model, but it suggests that our understanding of how quickly the first stars and galaxies formed may need refinement. The universe in its youth was perhaps more dynamic and efficient at forming structure than we previously thought. The end of the cosmic dark ages marked a transition from a universe dominated by gravity alone to one where light and radiation began to shape the environment. Stars didn't just sit passively in space. They heated the gas around them, blew powerful stellar winds, exploded in supernovae, and generally stirred things up. This feedback, the influence of stars on their surroundings, has played a crucial role in shaping the universe we see today. It regulated how and where new stars formed, enriched the gas with heavy elements, and helped sculpt the galaxies that would eventually emerge. As we trace this journey through cosmic history, we're watching the universe become more complex, more structured, more interesting with each passing era. From the smooth uniformity after recombination, to the first stars breaking the darkness, to the complex web of galaxies we see today, it's a story of emergence, of simple rules giving rise to beautiful complexity. The invisible universe. As astronomers began mapping the universe in greater detail throughout the 20th century, studying how galaxies move and how they're distributed through space, they encountered a profound mystery. Something didn't add up. The visible matter in galaxies, the stars and glowing gas clouds we can see, wasn't enough to explain what was happening. When you observe how fast stars orbit around the center of a galaxy, you can calculate how much mass must be present to hold them in their orbits. It's the same basic physics that explains how planets orbit the Sun. The gravity of all the mass inside a star's orbit pulls it inward, while the star's motion carries it forward, and these forces balance to create a stable orbit. By measuring how fast stars move at different distances from a galaxy's center, you can map out where the mass is. What astronomers found was shocking. In galaxy after galaxy, stars in the outer regions were moving far too fast. At those distances from the center, there shouldn't be enough visible mass to keep them in orbit. They should be flung outward into intergalactic space, the galaxy slowly evaporating as its outer stars escape. But that wasn't happening. The galaxies were stable and the stars stayed in their orbits. The only explanation was that there must be more mass present than we could see, a lot more, distributed throughout the galaxy, extending far beyond the visible stars. Was something invisible, something that exerted gravity but didn't emit light. Astronomers called it dark matter. At first, this idea met with skepticism. Maybe we were just miscounting the normal matter. Perhaps there were lots of dim stars we couldn't see, or clouds of gas too cool to glow. But as evidence accumulated from different types of observations, it became clear that dark matter was real and that it made up the majority of the matter in the universe. One particularly striking piece of evidence comes from gravitational lensing. Einstein's general relativity predicts that mass curves space, and when light passes through curved space, its path bends. Massive objects like galaxy clusters can act like giant lenses, bending and magnifying the light from more distant galaxies behind them. By studying how light is bent, we can map out where the mass is. When scientists did this for galaxy clusters, they found something extraordinary. The lensing effect was far stronger than could be explained by the visible matter alone. Even more remarkably, in some colliding galaxy clusters, they could separate out where the visible matter ended up from where the gravitational lensing and thus the total mass was strongest. The visible matter, mostly hot gas, slowed down and piled up in the collision. But the dark matter, which doesn't interact with normal matter except through gravity, passed right through. This provided direct visual evidence that dark matter was something fundamentally different from ordinary matter. So what is dark matter? The honest answer is, we don't know for certain. It's one of the greatest unsolved mysteries in physics. What we do know is that it's some form of matter that doesn't emit, absorb, or reflect light. It doesn't seem to interact through the electromagnetic force at all. It only interacts gravitationally, pulling on normal matter and bending light through its gravity. Leading candidates include hypothetical particles called WIMPs, weakly interacting massive particles which would be left over from the early universe. Another possibility is axions, extremely light particles that might exist in vast numbers. There are other, more exotic ideas as well. Scientists around the world are conducting experiments to detect dark matter directly, looking for the rare occasions when a dark matter particle might collide with an atom in a detector deep underground, shielded from other radiation. So far, despite decades of searching, no one has definitively detected a dark matter particle in the laboratory, but the gravitational evidence for its existence is overwhelming. About 85% of the matter in the universe appears to be dark matter. Only 15% is the ordinary matter that makes up atoms, stars, planets, and people. We are, in a very real sense, a minority component of the cosmos. Dark matter played a crucial role in the formation of structure in the universe. Because it doesn't interact with light, dark matter could begin collapsing under gravity earlier than normal matter. In the early universe, normal matter was coupled to radiation, pushed around by light, unable to collapse efficiently. But dark matter felt only gravity, and it began to clump and collapse long before recombination. It formed a kind of invisible scaffolding, a gravitational framework, and when normal matter finally became neutral and decoupled from radiation, it fell into the gravitational wells that dark matter had already dug. This is why galaxies exist where they do. The dark matter collapsed first, and the normal matter followed, falling into the same regions, lighting up as stars, making the dark matter structures visible to us. Without dark matter, the universe would look very different. There wouldn't be enough gravity to hold galaxies together or to form the large-scale structure we observe. The cosmic web of galaxies, the clusters and filaments, all of it traces the underlying distribution of dark matter. But dark matter isn't the only mysterious component of the universe. In the late 1990s, astronomers made another discovery that was, if anything, even more shocking. They were studying distant supernovae, using them as standard candles to measure cosmic distances and map out the expansion history of the universe. The expectation was that they would find the expansion slowing down over time, decelerated by the gravitational pull of all the matter in the cosmos. Instead, they found the opposite. The expansion wasn't slowing down. It was speeding up. The universe's expansion rate is accelerating, has been for billions of years, and shows no sign of stopping. This discovery was so unexpected that the team spent years checking and rechecking their data, worried they'd made a mistake. But the result held up, and in 2011 the leaders of these two research teams were awarded the Nobel Prize in Physics for discovering the accelerating expansion of the universe. What could cause this? Some force or property of space must be driving the acceleration, pushing the universe to expand faster and faster. This has been given the name dark energy, though that name is more of a placeholder than an explanation. We don't really know what it is. Dark energy appears to be a property of space itself. The more space there is, the more dark energy there is. As the universe expands, creating more space, it creates more dark energy, which drives even more expansion in a self-reinforcing cycle. It doesn't dilute as the universe grows, unlike matter, which gets spread thinner as space expands. The leading theoretical candidate for dark energy is the cosmological constant, the very same term Einstein added to his equations to keep the universe static and later called his biggest blunder. It turns out he may not have been wrong after all, just ahead of his time. A cosmological constant acts exactly like dark energy, a constant energy density associated with empty space that drives accelerated expansion. However, there's a significant problem. When physicists try to calculate what the value of the cosmological constant should be based on quantum field theory, they get an answer that's wrong by a factor of 10 to the power of 120, making it perhaps the worst theoretical prediction in the history of physics. This suggests we're missing something fundamental in our understanding of either quantum mechanics or gravity or both. Alternative theories propose that dark energy might not be constant but might change with time, a possibility called quintessence. Or perhaps our understanding of gravity itself needs to be modified on cosmic scales. Recent observations, including data from missions studying the cosmic microwave background and large-scale surveys of galaxies, are helping to narrow down the possibilities, but we're still far from a definitive answer. What we do know is that dark energy dominates the universe today. About 68% of the total energy content of the cosmos is dark energy. Add in the 27% that's dark matter, and you find that 95% of the universe is made of things we don't truly understand. All the stars, all the galaxies, everything we can see and touch, that's just 5% of what's out there. It's a humbling realization. For all our technological advancement, for all our scientific progress, the universe is still deeply mysterious. We're like explorers who've mapped the coastline but haven't yet ventured far inland. We know the dark matter and dark energy are there. We can measure their effects, but their fundamental nature remains hidden, waiting for new theories, new observations, new insights to illuminate them. The assembly of galaxies, with dark matter providing the gravitational scaffolding and normal matter falling into the potential wells it created. The universe began to assemble the grand structures we call galaxies. This wasn't a sudden process, but a gradual one, playing out over hundreds of millions of years, shaped by gravity, gas dynamics, and the complex interplay between different forms of matter and energy. The first proto-galaxies were small, irregular collections of stars and gas, nothing like the majestic spirals and ellipticals we see in the nearby universe today. They formed in the densest regions of the cosmic web, places where dark matter had already accumulated. As normal matter fell in, it heated up, radiating energy and eventually cooling enough to fragment and form stars. These early galaxies were cosmic construction sites, places of intense activity. Stars formed at rates much higher than in most galaxies today. The newly formed stars, especially the massive ones, poured out enormous amounts of energy in the form of ultraviolet radiation and stellar winds. When they died, they exploded as supernovae, heating the surrounding gas and blowing some of it out of the galaxy entirely. This feedback from stars played a crucial role in regulating galaxy growth. If stars formed too efficiently, too quickly, They would heat and disperse the gas so much that further star formation would be suppressed. Galaxies grew through a delicate balance between gas cooling and falling in on one hand, and energy from stars heating and pushing gas out on the other. Over time, these early proto-galaxies collided and merged with each other. When two galaxies meet, they don't collide like solid objects. Stars are so far apart relative to their size that even when two galaxies merge, individual stars almost never actually hit each other. Instead, the two systems gravitationally interact, their shapes distorting and eventually blending together to form a larger galaxy. These mergers were common in the early universe when galaxies were closer together and still growing. Each merger would trigger bursts of new star formation as clouds of gas collided and compressed, igniting new stellar nurseries. The shapes of galaxies were sculpted by these interactions, with repeated mergers often creating elliptical galaxies, while galaxies that grew more gradually through the accretion of gas tended to form rotating disk galaxies with spiral arms. Our own Milky Way galaxy is a spiral, a vast disk of stars about 100,000 light-years across, with a central bulge and several spiral arms winding outward. It contains somewhere between 200 and 400 billion stars, along with vast clouds of gas and dust. At its center lies a supermassive black hole, 4 million times the mass of the Sun, remarkably quiescent now, but perhaps more active in the past. The Milky Way didn't form in isolation. It's surrounded by dozens of smaller satellite galaxies, dwarf galaxies orbiting around it, some of which are being slowly torn apart and absorbed. And observations of stars in our galaxy's halo suggest that the Milky Way has consumed many other small galaxies throughout its history, growing larger through cosmic cannibalism. In fact, our galaxy is currently in the process of colliding with the Andromeda Galaxy, our nearest large galactic neighbor about 2.5 million light-years away. The two galaxies are approaching each other at about 100 kilometers per second, and in about 4 billion years they'll begin to merge. This will be a spectacular event, though any civilizations present to witness it will be in no danger. The stars are so far apart that actual collisions are vanishingly unlikely. Instead, the night sky will gradually fill with the stars and gas of Andromeda, the shapes of both galaxies distorting and eventually blending into a new, larger elliptical galaxy that astronomers have playfully nicknamed Milkomeda. On even larger scales, galaxies aren't distributed randomly through space, but are organized into a vast structure called the cosmic web. Imagine taking a three-dimensional map of all the galaxies in a large volume of space. What you'd see would look remarkably like a web or a foam. Galaxies cluster along vast filaments stretching across hundreds of millions of light-years. These filaments surround enormous voids, regions of space with very few galaxies. Where filaments intersect, you find galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. This web-like structure is a direct consequence of the distribution of dark matter. The dark matter itself is distributed this way, in filaments and clusters with voids between them, and the normal matter simply traces where the dark matter is. The pattern emerged from those tiny quantum fluctuations during inflation, amplified by billions of years of gravitational growth. Some of the largest structures we've identified include the Sloan Great Wall, a vast sheet of galaxies stretching across more than 1 billion light-years, and the Hercules Corona Borealis Great Wall, which may extend across 10 billion light-years. Those structures this large push the boundaries of what can form given the age of the universe. Within this grand cosmic architecture, galaxies come in many forms. Spiral galaxies like the Milky Way have distinct arms winding around a central bulge, regions where star formation is actively ongoing. Elliptical galaxies range from nearly spherical to elongated shapes, generally containing older stars with little ongoing star formation. Irregular galaxies have no clear structure, often appearing chaotic, frequently the result of gravitational interactions or mergers. And then there are peculiar galaxies, objects that defy easy classification, often caught in the act of merging or shaped by some unusual event. At the hearts of most large galaxies, including our own, lie supermassive black holes, objects with masses ranging from millions to billions of times the mass of the Sun. How these formed is still somewhat mysterious. Some may have grown from the collapse of the very first stars. Others might have formed from dense clusters of stars that collapsed together. Still others might have grown from smaller black holes that merged repeatedly over cosmic time. These central black holes aren't just passive objects. In many galaxies, especially in the early universe, they were actively feeding, pulling in vast amounts of gas and glowing brilliantly as the material heated to millions of degrees before crossing the event horizon. These active galactic nuclei, or quasars, were some of the brightest objects in the early universe, so luminous they could outshine their entire host galaxy. The energy they pumped into their surroundings profoundly influenced how their galaxies evolved, heating gas, driving winds, and regulating star formation. Today, most supermassive black holes, including the one at the center of the Milky Way, are quiet, dormant, having exhausted the easily accessible gas in their vicinity. But they still exert a gravitational influence on the stars around them, and occasionally they flare up when something, a star or a cloud of gas, ventures too close. The story of galaxy formation and evolution is still being written. New observations, particularly from telescopes like James Webb, are revealing galaxies in the early universe that challenge our models, that formed more stars more quickly than expected, that assembled more rapidly than we thought possible. Each discovery refines our understanding, adds new detail to the story, and sometimes raises new questions. What's clear is that galaxies are not static objects. They're dynamic, evolving systems shaped by gravity, star formation, supernova explosions, black hole activity, mergers, and interactions with their environment. They're cosmic ecosystems, places where matter cycles from gas to stars back to gas again, enriched with each generation of stars, gradually building up the chemical complexity that makes planets and life possible. The accelerating cosmos. For decades after Hubble's discovery that the universe is expanding, astronomers worked under the assumption that this expansion must be slowing down. It seemed obvious. The universe is filled with matter, and matter generates gravity, and gravity pulls things together. So even though space might be expanding now, the mutual gravitational attraction of all the galaxies should be acting like a brake, gradually slowing the expansion. The only question was whether there was enough matter to eventually halt the expansion altogether and perhaps cause a collapse, or whether the expansion would continue forever, just at an ever-decreasing rate. To answer this question, astronomers needed to measure how the expansion rate has changed over time, and to do that, they needed a way to measure vast cosmic distances very accurately. They found it in a particular type of stellar explosion called a type winner supernova. These supernovae occur when a white dwarf star, the dense remnant of a dead star, accumulates enough mass from a companion star to reach a critical threshold called the Chandrasekhar limit, about 1.4 times the mass of our Sun. At this point, the white dwarf can no longer support itself and collapses, triggering a runaway fusion reaction that completely destroys the star in a brilliant explosion. The key property that makes type Ia supernovae useful is that they always explode at the same mass, and therefore they always release roughly the same amount of energy, making them about the same intrinsic brightness. This means if you see a type Ia supernova that appears dim, it's because it's far away. If it appears bright, it's closer. By measuring how bright they appear and comparing that to how bright they actually are, you can calculate the distance. Astronomers call them standard candles. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to use type Ui supernovae to map the expansion history of the universe. They searched for these explosions in distant galaxies, billions of light years away. Events that happened billions of years ago. By measuring their distances and their redshifts, they could determine how fast the universe was expanding at different times in its history. What they found shocked everyone, including themselves. The distant supernovae were about 10% fainter than expected. This meant they were farther away than they should be if the expansion was slowing down. The only explanation was that the expansion of the universe has been speeding up. Something was causing the universe to expand faster and faster over time. This was such an unexpected result that both teams spent years checking their analysis, searching for systematic errors, anything that might explain it away. But the result held up. Other observations confirmed it. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rice, the leaders of these projects, were awarded the Nobel Prize in Physics for their discovery of the accelerating expansion of the universe through observations of distant supernovae. The discovery of acceleration implies the existence of dark energy. Though remember, that's just a name for whatever is causing the effect. It doesn't tell us what it is. Dark energy appears to act like a repulsive form of gravity, pushing space to expand rather than pulling it together. And unlike matter, which gets more diluted as the universe expands, dark energy seems to maintain a constant density. As space grows, more dark energy appears, driving ever more expansion. The simplest explanation for dark energy is Einstein's cosmological constant, a property of empty space itself that causes it to expand. But as mentioned earlier, there's a huge problem with this idea. When quantum physicists try to calculate what the vacuum energy should be, they get an answer that's wildly, absurdly wrong, off by more than 100 orders of magnitude. This is called the cosmological constant problem, and it represents a profound gap in our understanding. Recent observations have added new wrinkles to this mystery. Some studies, including recent data from the Atacama Cosmology Telescope, have suggested that dark energy might not be perfectly constant, but could be changing with time, perhaps evolving as the universe ages. If true, this would rule out the simple cosmological constant and point towards something more dynamic, possibly a new field permeating space that changes over cosmic history. Other measurements, however, suggest the cosmological constant model works just fine. There's currently a tension in the data, different methods of measuring the expansion rate producing slightly different results. This could mean there are systematic errors in some measurements, or it could hint at new physics we don't yet understand. Astronomers and cosmologists are working to resolve this tension, and the answer will have profound implications for our understanding of the universe. What's clear is that dark energy dominates the universe today and will increasingly dominate in the future. Currently, about 68% of the total energy content of the cosmos is dark energy, while matter, both dark and normal, makes up the remaining 32%. But because dark energy doesn't dilute while matter does, the fraction that's dark energy will grow over time. This has profound implications for the future evolution of the universe. Galaxies that aren't already bound together by gravity will move farther and farther apart, accelerated by dark energy. Eventually, galaxies beyond our local group, the collection of a few dozen galaxies that includes the Milky Way and Andromeda, will recede so far and so fast that their light will never reach us. They'll slip beyond what's called the cosmic horizon, forever cut off from our observable universe. In the far future, trillions of years from now, intelligent beings living in the Milky Way or its successor galaxy, after merging with Andromeda, would look out and see a very different night sky. The distant galaxies would have vanished, receded beyond sight. The cosmic microwave background would have been stretched to such long wavelengths that it would be essentially undetectable. The evidence that the universe had a beginning, that there are other galaxies, that space is expanding, all of it would have been erased by the relentless acceleration of space. Those future astronomers, if they existed, would have no way to discover the Big Bang or the expansion of the universe through direct observation. They would see only their own galaxy, isolated in an apparently empty cosmos, unless they were fortunate enough to have preserved our current knowledge. It's a sobering thought, a reminder that we're living in a special time cosmologically, an era when the universe is old enough to have formed galaxies and life, but young enough that we can still see evidence of its origins. The discovery of dark energy also raises deep questions about the ultimate fate of the cosmos. If dark energy remains constant or grows stronger, the universe will expand forever, cooling and thinning until it approaches a state of maximum entropy. A cold, dark, almost featureless expanse. But if dark energy can change, if it could weaken or even reverse, then other futures become possible. The expansion might slow, perhaps even reverse into a contraction, or dark energy might grow stronger, eventually tearing apart galaxies, stars, planets, even atoms in a scenario called the Big Rip. We don't know which future awaits. The nature of dark energy, whether it's constant or changing, stable or evolving, that's one of the biggest open questions in cosmology. Answering it will require more observations, more data, larger surveys of galaxies, more precise measurements of the cosmic microwave background, and perhaps new telescopes we haven't even built yet. What we do know is that we live in an accelerating universe, one that's expanding faster now than it did in the past, driven by a mysterious energy that fills all of space. It's a strange, beautiful, unsettling discovery, one that reminds us how much we still have to learn about the cosmos we inhabit. Possible endings. When we peer far into the future, beyond the lifetimes of stars, beyond the fate of galaxies, we enter the realm of deep cosmological speculation. The ultimate fate of the universe depends critically on the nature of dark energy and the laws of physics at the largest scales, things we don't yet fully understand. But we can sketch out several possible scenarios, different endings to the cosmic story that began with the Big Bang. The most widely accepted scenario, given current observations, is sometimes called the Big Freeze, though it's also known as heat death. In this future, the expansion of the universe continues forever, driven by dark energy. Over trillions of years, far longer than the current age of the universe, star formation gradually winds down as the supply of gas in galaxies is exhausted. Existing stars burn through their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. Eventually, perhaps 100 trillion years from now, the last stars will fade. The universe will enter what's called the degenerate era, dominated not by shining stars but by stellar remnants. These dead stars will slowly cool, radiating away their remaining heat into the expanding darkness. Galaxies, now dark and invisible except for their gravitational influence, will drift farther apart, carried by the accelerating expansion. Over even longer timescales, the remaining structures will begin to evaporate. Random gravitational encounters between stellar remnants will occasionally fling some objects out of their galaxies. Others will spiral inward, eventually falling into the supermassive black holes at galactic centers. These processes are incredibly slow, but given enough time, a lot of time, perhaps 10 to the power of 19 years, galaxies will gradually dissolve. Even black holes aren't eternal. Stephen Hawking showed that black holes should slowly evaporate through a quantum process now called Hawking radiation. The larger the black hole, the slower this process, but given enough time, all black holes will eventually evaporate completely. For a supermassive black hole, this might take 10 to the power of 100 years or longer. When the last black holes finally evaporate, the universe will be left with a thin soup of elementary particles, photons, neutrinos, electrons, perhaps quarks, and other particles, spread across ever-expanding space. Eventually, if the universe expands forever, it will approach a state of maximum entropy, a condition where energy is spread so uniformly that nothing interesting can happen anymore. No stars can form, no life can exist, no complex structures of any kind, just particles drifting farther and farther apart through cold, dark space. It's not a dramatic ending, no catastrophe or explosion, just a long, slow fade into silence and stillness. The Big Freeze is in many ways the loneliest of all possible endings. But there are other possibilities. If dark energy isn't constant, if it grows stronger over time, the universe could face a much more violent end. This scenario is called the Big Rip, and it's based on the idea that dark energy might not just maintain a constant density, but might actually increase in strength as the universe ages. In this scenario, the acceleration of the universe's expansion doesn't just continue, it gets faster and faster. At first, this would look similar to the Big Freeze. Distant galaxies recede, stars die, structures dissolve. But eventually the acceleration would become so extreme that it starts to tear things apart. First, galaxy clusters would be pulled apart, individual galaxies separating from each other at ever-increasing rates. Then galaxies themselves would be torn apart, stars ripped away from each other despite their gravitational bonds. As the acceleration continues to grow, solar systems would be disrupted, planets torn from their orbits around their stars. Eventually, stars themselves would be ripped apart, their gravity unable to hold them together against the accelerating expansion. In the final moments, perhaps just minutes before the end, The expansion would become so rapid that even atoms would be torn apart. Molecules would break first, then atomic nuclei, and finally even protons and neutrons would be shredded into their constituent quarks. The universe would end not with a freeze, but with everything being torn into its most fundamental pieces. The timescale for the Big Rip, if it happens at all, is uncertain. Different models suggest anywhere from 22 billion years to hundreds of billions of years in the future. Current observations don't strongly favor the Big Rip scenario, but they don't rule it out either. The behavior of dark energy over time is something we're still trying to measure. A third possibility, one that's become less likely given the discovery of dark energy but hasn't been completely ruled out, is the Big Crunch. This would occur if the expansion of the universe eventually reverses. Perhaps dark energy weakens, or perhaps there's more matter in the universe than we've accounted for. If the expansion slows, stops, and then reverses, the universe would begin contracting. At first, this contraction would be gentle, imperceptible. Distant galaxies would start showing blue shifts instead of red shifts as they approached rather than receded. Over billions of years, galaxies would draw closer together. As the contraction accelerated, collisions between galaxies would become more common. The cosmic microwave background, instead of cooling with expansion, would heat up as space contracted, shifting from microwaves to infrared to visible light. Eventually, the entire universe would be compressed back down, temperatures rising, structures being destroyed. Stars would be torn apart by tidal forces as galaxies collided. The background radiation would become so hot that it would vaporize any remaining structures. Space would become opaque again as atoms were ionized. Finally, the universe would return to a hot, dense state similar to the moments after the Big Bang, perhaps ending in a singularity, or perhaps transitioning into something else entirely. This leads to a fourth possibility, one that's more speculative but captures the imagination. What if the Big Crunch isn't really an ending but a transition? What if, instead of collapsing to a singularity and stopping, the universe bounces, rebounding into a new phase of expansion? This is the idea behind cyclic or oscillating universe models. In these scenarios, the universe goes through repeated cycles of expansion and contraction, each Big Crunch giving birth to a new Big Bang. Perhaps our universe is just one cycle in an eternal series, stretching infinitely into both the past and the future. Each cycle might last hundreds of billions of years, but over infinite time, there would be infinite cycles. Some versions of this idea, like those based on loop quantum cosmology, suggest that quantum effects prevent the formation of a true singularity. Instead, the collapsing universe reaches a minimum size where quantum repulsion becomes strong enough to halt the collapse and trigger a rebound. The Big Bang wouldn't be the absolute beginning, but rather a transition point between a previous contracting phase and our current expanding phase. Other cyclic models, inspired by string theory, imagine a universe bouncing between different states or even multiple universes colliding in higher dimensions, each collision sparking a new Big Bang in one of the universes. These ideas push the boundaries of current physics and venture into realms that are difficult or impossible to test with current technology. The appeal of cyclic models is partly philosophical. They avoid the question of what came before the Big Bang by saying there was something before, another cycle. They avoid the need for an absolute beginning. But they also raise new questions. If the cycles repeat, do they repeat identically? Does each cycle have the same laws of physics, or do they vary? Is information carried from one cycle to the next, or is each cycle a fresh start? Current observations favor an eternally expanding universe, something closer to the Big Freeze scenario, but we can't yet rule out these other possibilities with absolute certainty. The nature of dark energy remains mysterious, and our understanding of physics at the most extreme conditions, the kind that might exist at a big crunch or at the moment of the Big Bang, is incomplete. What's remarkable is that we can even ask these questions. That we can use observations of distant galaxies and precise measurements of the cosmic microwave background to constrain what might happen trillions of years in the future, or what might have happened before the beginning. We're using science to peer not just across vast distances, but across vast spans of time, from the first moments after the Big Bang to the ultimate fate of the cosmos, whichever ending awaits. If any of these scenarios is correct, it won't happen for an incredibly long time, far longer than the universe has already existed. We're living in a young universe, cosmically speaking, an era of stars and galaxies, of complexity and structure. The long decline into heat death or the dramatic violence of a big rip or big crunch are all in the distant future, so distant that they're almost abstract. But contemplating these endings reminds us of something important. The universe is not static. It had a beginning. It's evolving now. And it will have a future that looks different from the present. We're witnessing a moment in cosmic history, a chapter in a much longer story. And while we may never know how that story ends, we're fortunate to be here, conscious and curious, able to read the pages that have been written and to speculate about those yet to come. Our place in cosmic time. As we've journeyed from the first moments after the Big Bang through billions of years of cosmic evolution, it's worth pausing to consider where we, humanity, fit into this grand narrative. We exist at a specific moment in the universe's history, neither at the beginning nor anywhere near the end, and our perspective is shaped by that position. The universe is 13.8 billion years old. Our solar system formed about 4.6 billion years ago, when the universe was already more than 2/3 of its current age. The first stars had long since lived and died. Several generations of stellar life cycles had already enriched the cosmos with heavy elements. The first galaxies had formed, merged, and grown into structures like the Milky Way. In other words, the universe had to mature for billions of years before a planet like Earth could even form. The primordial hydrogen and helium from the Big Bang couldn't make rocky planets or living things. We needed carbon, oxygen, nitrogen, iron, and all the other elements that stars create through fusion and scatter through supernova explosions. We are, quite literally, made of stardust, assembled from atoms that were forged in stellar cores and blasted into space by dying stars. Life on Earth emerged relatively quickly after the planet formed, with the first simple organisms appearing perhaps 3.8 billion years ago, not long after the surface cooled enough and the bombardment by asteroids and comets subsided. But complex multicellular life took much longer to develop. Animals only appeared in the fossil record about 600 million years ago. Humans, modern humans, emerged only in the last few 100,000 years. On a cosmic timescale, we're incredibly recent arrivals. If you compress the entire history of the universe into a single year, with the Big Bang happening at the stroke of midnight on January 1st, the solar system wouldn't form until early September. The first dinosaurs wouldn't appear until late December. all of recorded human history would fit into the last few seconds before midnight on December 31st. We exist in what you might call the universe's golden age, a time when stars are plentiful, when galaxies are still forming new stars, when the cosmos is rich with structure and complexity. This won't last forever. As we discussed, the universe is headed toward a much quieter, darker future. In trillions of years, star formation will have mostly ceased. But we're here now, in this flourishing epoch, able to witness a universe full of light and activity. There's also a remarkable coincidence in our timing. We live at a moment when the universe is old enough that we can see evidence of its origins, the cosmic microwave background, the abundances of light elements, the expansion of space, but young enough that this evidence hasn't been erased or rendered undetectable by billions more years of expansion and evolution. Future civilizations, if they exist, might not have access to the clues we have. Our technological development has also aligned with a unique window of observational opportunity. We've developed telescopes and instruments capable of detecting the faint signals from the early universe, just as those signals are still accessible a few billion years earlier. And intelligence might have evolved on planets where the universe looked very different, still dominated by quasars and violent galaxy mergers. A few trillion years later, and the evidence of the Big Bang might be gone. The cosmos, a darker, emptier place. From a different perspective, we're also living at an interesting point in Earth's history. Our sun is about halfway through its lifespan. It will continue to burn for another 5 billion years or so, before swelling into a red giant and destroying the inner planets, including Earth. Life on Earth probably has about 1 billion years left before the sun gets hot enough to boil away the oceans. That's a long time by human standards, more than twice as long as life has already existed on Earth, but it's finite. And of course, there's the more immediate context of human civilization itself. We've only been studying the universe scientifically for a few centuries. The Big Bang theory is less than a century old. Our ability to detect the cosmic microwave background, to find distant supernovae, to image galaxies billions of light years away. All of this is even more recent, developed mostly in the last few decades. We're the first generation of humans to truly understand where we came from in a cosmic sense. To know that we're living in an expanding universe that emerged from a hot, dense state billions of years ago. To see ourselves as part of a continuous story of matter and energy, unfolding over vast spans of time. Previous generations had myths and philosophies, valuable in their own ways, but we have something else, a narrative based on observation and mathematics, tested against the universe itself. This knowledge brings with it a particular kind of perspective. When you understand that the atoms in your body were forged in stars, that the patterns of galaxies trace back to quantum fluctuations during inflation, that everything you see is part of an evolving cosmos with a history and a future, it changes how you see yourself and your place in the world. We're not separate from the universe looking in. We're part of it. We're one way that the universe has organized itself. One particular arrangement of matter that's become complex enough to contemplate its own origins. We're the universe becoming self-aware, at least in this small corner of space, and for this brief moment in time. There's something both humbling and empowering about this realization. Humbling because we're so small, so recent, so temporary in the vast sweep of cosmic time. Our entire species might exist for just a few million years in a universe that will continue for trillions. We inhabit one planet among billions in one galaxy among hundreds of billions. On cosmic scales, we're almost negligibly small, but empowering because despite our smallness, we've managed to figure out so much. We've looked at the light from distant galaxies and determined the age of the universe. We've detected radiation from when the cosmos was just 380,000 years old. We've traced the chain of events from the Big Bang to the present, from the first atoms to the first stars, to the complex chemistry that makes life possible. We've done all this in just a few human lifetimes of dedicated scientific work, and we're still learning. Every new telescope, every new observation, every new experiment adds to our knowledge. The James Webb Space Telescope is showing us galaxies from the cosmic dawn, from when the universe was just a few 100 million years old. Gravitational wave detectors are listening for ripples in space-time from colliding black holes and neutron stars. Particle physics experiments are searching for dark matter and probing the fundamental nature of reality. The story isn't finished. We don't know what dark matter is. We don't understand dark energy. We haven't unified quantum mechanics and general relativity. We don't know if there are other universes beyond our own. We don't know if we're alone or if life and intelligence have emerged elsewhere in the cosmos. These are open questions, mysteries waiting to be solved by future generations of scientists using tools and techniques we haven't even invented yet. In this sense, we're living in an age of discovery, a time when our understanding of the universe is expanding rapidly, when new questions are being asked and new answers are being found. It's an exciting time to be curious about the cosmos, to wonder about our origins and our future. The deepest questions. As we near the end of our journey through cosmic history, it's worth reflecting on some of the deepest questions that remain. Questions that sit at the intersection of physics, philosophy, and maybe even something beyond what either discipline can fully address. Perhaps the most fundamental question is simply, why is there something rather than nothing? The Big Bang Theory tells us how the universe evolved from a hot, dense state, but it doesn't really explain why that hot, dense state existed in the first place. What caused the Big Bang? What, if anything, came before it? Some physicists have proposed that the universe could have emerged from nothing through a quantum fluctuation, that the laws of quantum mechanics allow for such a thing to spontaneously appear. In quantum mechanics, particles can pop into existence for brief moments, borrowing energy from the vacuum and then disappearing again. Perhaps the entire universe is something like that, a quantum fluctuation that happened to be stable and long-lived. But this just pushes the question back a step. Why do the laws of quantum mechanics exist? Why those laws and not others? Why do the fundamental constants of nature have the values they do? The strength of gravity, the mass of the electron, the speed of light? These numbers seem arbitrary, but if they were even slightly different, the universe would look dramatically different. And life as we know it probably couldn't exist. This observation has led some scientists to propose the anthropic principle, the idea that we observe the universe having properties compatible with life, because if it didn't, we wouldn't be here to observe it. It's a kind of selection effect. We necessarily find ourselves in a universe capable of producing observers. Some take this further and propose the multiverse hypothesis. Perhaps our universe is just one of many, each with different laws of physics and different values for the fundamental constants. Most of these universes would be sterile, unable to form stars or galaxies or life. But in the vast ensemble, some universes would have the right properties, and we happen to live in one of those because those are the only ones where life can ask the question. The multiverse is a controversial idea. It's difficult or impossible to test because, by definition, other universes are causally disconnected from ours. We can't see them or interact with them. Critics argue that it's not really science if it can't be tested. Proponents counter that it emerges naturally from certain theories, like inflation, which suggests that different regions of space could have inflated differently, creating pocket universes with different properties. Whether the multiverse exists or not, we're still left with questions. Why does anything exist at all? Why are there laws of physics? Why is the universe comprehensible, governed by mathematical principles we can discover and understand? The physicist Eugene Wigner once wrote about what he called the unreasonable effectiveness of mathematics in the natural sciences. The surprising fact that mathematical equations, abstract constructs of human thought, describe the physical world so accurately. Why should the universe be mathematical? Why should the laws of physics be expressible in equations we can write down and solve? Some philosophers and physicists have suggested that mathematics doesn't just describe the universe but is the universe. That physical reality is fundamentally mathematical in nature. Others maintain a distinction between the map and the territory, between our mathematical descriptions and the underlying reality they describe. This is a question that probably goes beyond what science alone can answer. Another deep question concerns consciousness and the role of observers in the universe. Quantum mechanics, with its peculiar requirement that systems exist in superpositions of states until measured, raises questions about what constitutes a measurement and whether consciousness plays a special role. Most physicists don't think consciousness is necessary for quantum collapse. That any sufficiently complex interaction counts as a measurement. But the questions persist. And then there's the question of whether we're alone. In a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars, many with planets, it seems almost inconceivable that Earth is the only place where life has emerged. The chemical ingredients for life, carbon, hydrogen, oxygen, nitrogen, are abundant throughout the cosmos. The processes that led to life on Earth, chemical evolution in the presence of energy sources, don't seem to require anything exotic or unlikely. Yet we've found no evidence of life beyond Earth. No radio signals from alien civilizations. No artifacts in our solar system. No biosignatures in the atmospheres of distant planets. Though our ability to detect such things is only now becoming sophisticated enough to have a real chance. This is Fermi's paradox. If life is common, where is everybody? Possible answers range from the optimistic, maybe life is common, but intelligent technological civilization is rare or short-lived, to the sobering, maybe we're truly alone, the first or only intelligence in the observable universe. We don't know. But as we develop better telescopes and search more planets, we may finally answer this question, one of the oldest and most profound humanity has ever asked. The nature of time itself is another deep mystery. Our current physics treats time as a dimension somewhat like space, but our experience of time is very different from our experience of space. We remember the past, but not the future. We experience time flowing in one direction, always forward, never back. Why? The laws of physics, at least at the fundamental level, are time symmetric. They work the same way, running forward or backward. Yet the universe clearly has an arrow of time, a direction. This seems to be related to entropy, the tendency of systems to become more disordered over time. The second law of thermodynamics says entropy always increases or stays the same, never decreases. But why was entropy so low in the early universe? Why did the Big Bang start in such an ordered state? This is another question we don't have a complete answer to. And finally, there's the question of the ultimate nature of reality. Is space and time fundamental, or do they emerge from something more basic? String theory suggests that what we think of as particles are actually tiny vibrating strings, and that space might have more dimensions than the three we experience. Loop quantum gravity suggests that space itself is quantized, made of discrete chunks at the smallest scales. We don't know which, if any, of these theories is correct. We don't know if there's some deeper level of reality beneath what we've discovered, some more fundamental description waiting to be found. The history of physics is a history of peeling back layers, finding that things we thought were fundamental are actually made of smaller pieces or are aspects of deeper principles. Will this continue forever, or is there a bottom, a final theory of everything? These questions might seem abstract, removed from everyday life, and in one sense they are. Whether the universe had a beginning or has always existed doesn't change how you live your day-to-day life. Whether we're alone in the cosmos or surrounded by life doesn't immediately affect your commute or your relationships. But in another sense, these questions are deeply human. We're the species that asks why. We look up at the night sky and wonder. We probe the limits of knowledge, not because we have to, but because we're curious. Because understanding the universe feels meaningful and important in some fundamental way. These questions are part of what makes us human, part of what makes us conscious beings capable of contemplating our own existence. And perhaps the most remarkable thing is not that we can't answer all these questions, but that we can answer any of them, starting from basic observations, from the redness of distant galaxies and the temperature of the cosmic microwave background. We've reconstructed the history of the universe back to moments after its beginning. That's astonishing. That's something worth celebrating even as we acknowledge how much we still don't know. The continuing story. As we come to the end of our journey through cosmic history, from the Big Bang to the present and glimpses of the future, it's worth remembering that this isn't really the end of the story. It's just the end of our current understanding, a snapshot of where science stands in this moment of time. The universe is still evolving, still expanding, still creating and destroying, still unfolding according to the laws of physics across vast reaches of space and time. New stars are being born in clouds of gas. Old stars are dying in spectacular explosions. Black holes are merging, sending ripples through space-time. Galaxies are colliding and reshaping each other. Dark energy is pushing everything apart, and on at least one planet orbiting an ordinary star in an ordinary galaxy. Conscious beings are looking up and trying to understand it all. We're using our telescopes and detectors, our mathematics and theories, to piece together the story of where we came from and where we might be going. Every observation adds another piece to the puzzle. Every experiment tests our theories. Every new discovery raises new questions even as it answers old ones. In the coming years and decades, we'll learn more. Better telescopes will show us even earlier galaxies, perhaps finally seeing the very first stars to form in the universe. Gravitational wave detectors will reveal events we've never witnessed before, cosmic collisions and exotic objects we can barely imagine. Particle physics experiments might finally detect dark matter or discover new fundamental particles. Theoretical breakthroughs might unify quantum mechanics and general relativity, or explain the nature of dark energy. Or we might be surprised by something completely unexpected, some discovery that forces us to rethink everything we thought we knew. That's happened before in the history of science. The discovery of dark energy, for instance, was a complete surprise, something no one predicted. Who knows what other surprises the universe has in store? What's certain is that humans will keep looking, keep wondering, keep trying to understand. It's part of our nature. We're not content to simply exist without understanding. We want to know why, to grasp the patterns, to see the connections. We want to understand our place in the cosmos. And maybe there's something poetic about that. The universe began as a hot, dense, undifferentiated state, about as simple and uniform as anything can be. Over billions of years, it evolved, became more complex, formed structures on every scale from atoms to galaxy superclusters, and eventually, at least in one small corner, it became complex enough to become conscious, to look back at itself, to comprehend its own history. We are made of atoms forged in the hearts of stars, organized by evolution and chemistry into thinking, feeling beings. We're matter that's become aware of itself, stardust contemplating the stars. When you look up at the night sky and wonder about the cosmos, you're participating in something extraordinary, the universe understanding itself. Our individual lives are brief, just a few decades in a universe billions of years old. Our entire species might last only a geological moment. But in this moment, we have the privilege of knowledge, of understanding, of being able to tell the story of the universe from its fiery beginning to the present day. We can look at a distant galaxy and know that we're seeing it as it was billions of years ago. We can detect the faint echo of the Big Bang still resonating through space. We can calculate what will happen trillions of years in the future. That's remarkable. That's precious. That's something worth cherishing and preserving and passing on to future generations. The knowledge we've gained about the cosmos is part of our heritage as a species, part of what makes us human. So as we close this journey through space and time, take a moment to appreciate where we are. You're alive in a universe of extraordinary beauty and complexity, a cosmos that somehow gave rise to consciousness and curiosity. You're part of an ancient and ongoing story, connected to everything that came before and everything that will come after. The atoms in your body are billions of years old, cycled through stars and planets and living things. The light that's hitting your eyes right now started its journey from distant stars, years or even millions of years ago. You're breathing air that contains atoms that were once part of dinosaurs, of ancient trees, of the first organisms to ever live. You're connected to all of it, part of the same cosmic web that stretches across space and time. And now, as you hopefully drift off to sleep, as your thoughts settle and your breathing slows, you can rest knowing that you're part of something vast and magnificent. The universe that began nearly 14 billion years ago in a flash of heat and light has evolved to include you, your thoughts, your dreams, your wonder at it all. If you've enjoyed this journey through the cosmos, if it's helped you see the universe a little differently, or appreciate the beauty of science and discovery. I hope you'll consider subscribing to Behind the Space and liking this video. It helps others find these explorations of the universe we call home. Thank you for joining me on this journey through cosmic history. The stars are still shining. Galaxies are still spinning. The universe is still expanding, still evolving, still full of mysteries waiting to be discovered. And somewhere in all of that vastness, on a small blue planet orbiting a yellow star, you exist, conscious and curious, able to contemplate the cosmos that created you. Rest well, fellow traveler through space and time. The universe continues its ancient dance, and tomorrow there will be more wonders to discover, more questions to ask, more of this magnificent story to explore. For now, sleep soundly, knowing you're part of something extraordinary, something ancient and ongoing, something that connects you to the furthest reaches of space and the earliest moments of time.